Hi, everybody, and welcome to Lesson 5 from Unit 5, which is about the second derivative test. Now, if the title of this lesson sounds a little bit familiar, it's because we've already learned about something called the first derivative test. And that was when we were able to use the sign changes in the first derivative to determine where our function had relative or local maxima and minima. In today's lesson, we have one learning target, and today's learning target is I can use the second derivative to determine whether a critical point is the location of a relative or local max or min. So, what we're going to be doing today is identifying relative extrema, just like we did before, but using a different technique where we're going to be using the second derivative now to identify relative extrema instead of a sign chart where we can look at the first derivative. Here's what the second derivative test says. We can use the second derivative to determine if a critical point, and this is important, it's a critical point, is a max, a min, or neither. And here's how it works. So this is really important. It has to be a critical point to start with before we then look at the second derivative to determine if that's a max, a min, or neither. So we start with a critical point and we use the second derivative to kind of narrow it down to what type of extrema, if any, would occur at that value. So you'll notice that both pieces of this kind of test start with suppose that the first derivative is equal to 0 or does not exist. Now, by starting with that, by supposing that the first derivative is equal to 0 or does not exist, it tells you that we're either going to have a place where there's a horizontal tangent line, so it's at the top or the bottom of like a hill or a valley, or there's going to be some sort of like a corner there, or a cusp there, or a vertical tangent line there. So we're going to be looking at a place where kind of the first derivative is already going to be a 0 or a does not exist. And that applies for both of these. We're already going to have one of these pictures going on. If the first derivative is 0 or does not exist, and the second derivative is positive. Now remember, we're looking at the second derivative here. The second derivative being positive means that my function is concave up. So I know that now my graph is concave up. And I know that my first derivative is already 0 or does not exist. Well, the only one of these pictures where the function is concave up and the first derivative is 0 or does not exist would be this one. So by knowing that the first derivative is 0 or does not exist and the second derivative is greater than 0, we know for sure that we have a picture that looks like this, and we specifically located this spot on that graph where there's like a horizontal tangent line, for example, and that's going to be a minimum. Now let's say we change our definition here a little bit, and instead of the second derivative being positive, we have a second derivative that's negative, which means our function is concave down. Now we're going to have a graph that's concave down like a frown, and it's going to be a place where the first derivative is 0 or does not exist. So it would have to be right here at the top, which means we're going to have a maximum. Here's an example or a couple examples of where you would want to use this test. So when would this be appropriate? Let's say that we're given this function and we're asked, does f of x have a maximum, a minimum, or neither, specifically at x equals 1? So I'm not asking you to find where are all of the maximums and where are all of the minimums, but just what's happening specifically at x equals 1. Well, when that happens and you have a specific x value to test, the first thing that I would do is find the first derivative of our function and plug in that number. So let's find the first derivative. If we find the first derivative, the derivative of negative x would be negative 1. The derivative of e to the something is just e to the something, but we need to apply chain rule here The derivative of 1 is 0, and the derivative of negative x is negative 1. So the chain here is negative 1. What that means is that I can simplify this equation to negative 1 plus e to the 1 minus x. Now the next step is I'm going to take this specific x value, which in this case I'm talking about the number 1, and I'm going to plug that number into my first derivative. Because in order to have any kind of a max or a min, the first derivative needs to have a critical point, so a place where it's equal to 0 or undefined. So if I plug in the number 1, I get negative 1 plus e to the 1 minus 1. E to the 1 minus 1 would be 0, so I would have negative 1 plus e to the 0, which would be negative 1 plus 1, which is 0. Since my first derivative is equal to 0, it tells me that I have a critical point at x equals 1 because the first derivative was equal to 0. Now, in order to determine if that's a max or a min or neither at that spot, I'm going to find the second derivative and see what's happening. So I'm now going to take my original function and I'm going to find the second derivative. So I'm going to start here because that was my simplified first derivative. So my second derivative would be the derivative of negative 1 is 0. So I'm just going to take the derivative of e to the something, which would be e to the something, times the chain rule, which just like before would be negative 1. So my simplified second derivative would be negative e to the 1 minus x power. Now I'm going to take that number, the positive 1, and I'm going to plug it in there as well. When I plug in the number 1 to the second derivative, I get negative e to the 1 minus 1. And 1 minus 1 is 0. So I get negative e to the 0, which would simplify to negative 1. Since I get negative 1, it tells me that my function is concave down. Well, if my first derivative is 0 and my function is concave down, then based on this visual, there must be a max. So I would say f of x has a maximum at x equals 1 because the first derivative, when I plug in the number 1, is 0, which makes it a critical point. And the second derivative, when I plug in the number 1, that should say 1, is less than 0. So in other words, it's negative, so my function is concave down. And that would be my final answer. Now let's do the exact same thing. So we're working with the same function, but I want to know what's happening when x is 0. Now I've already got my derivative figured out, so I'm not going to re-go through the process of figuring out the derivative. I'm just going to use the equation I already found up here, and I'm going to plug in the number 0 this time. If I plug in the number 0, I get negative 1 plus e to the 1 minus 0. Now, e to the 1 minus 0 would just be e to the 1, so I get negative 1 plus e. Now, this is not equal to 0, which means f of x does not have a critical point at x equals 0. As soon as I find that out, as soon as I know I don't have a critical point, my derivative is not equal to 0 and it's not undefined, I'm going to stop. There can't be either a max or a min here because I don't have a derivative that's equal to 0. So my final answer here is just going to be f of x has neither a max or min at x equals 0 because f prime of 0 is not equal to 0 and is also not undefined. So what I wanted to do here is show you an example where you do have a critical point, so then you need to go to the second step and find the second derivative to determine whether that's a max or a min, and also an example where you don't have a critical point, and so you stop because you can't have a max or a min, it's going to be neither. Now, the next thing that I wanted to talk about is how we can show this and kind of use this in a problem where we might be dealing with a slightly different kind of function. In this case, a function that has implicitly defined functions and derivatives. So in this third problem here, it says find the value of the second derivative and determine whether the curve has a local max, a min, or neither at the point 3, 2. Let's start with the first part of these instructions, which is just find the second derivative. So they're being very specific. Find the second derivative. So let's do that first before we worry about whether there's a max, a min, or neither and how we would approach that. To find the second derivative, I'm going to need to use quotient rule. So d squared y over dx squared would be equal to low, which is 8y minus 3x, d high, so the derivative of the top would be 3 dy over dx minus 2. So low d high minus high, which is 3y minus 2x, d low. So I would write 8 dy over dx minus 3. And low squared, which in this case would be 8y minus 3x squared, goes down below. Now, the next thing that I'm going to do here is I'm going to replace all of these dy over dx's with this equation that I've already got up here for the derivative. So what I'm going to have here, and I'm not going to simplify this, it doesn't say I need to write this in the most simple form, so I'm not going to bother, is I'm going to have 3, and then I'm going to plug in the 3y minus 2x over 8y minus 3x. And again, I'm not simplifying. I'm just plugging in the values. Minus, and I'm going to have 3y minus 2x, parentheses 8. Now I'm going to substitute that in. So I'm going to have 3y minus 2x over 8y minus 3x minus 3 all over the 8y minus 3x squared. Okay, so step 1 is done. I found the second derivative. The second part of this question says, determine whether the curve has a local max, min, or neither at the point 3, 2. Now, since I'm dealing with a specific value here, it doesn't say find all the maximums and all the minimums. I'm going to go ahead and just check out what's happening specifically at that value. So to do this, step number 1 is going to be to plug in those values into the first derivative. Because remember, the first step is we've got to have a critical point. The first derivative has to be equal to 0 or undefined. If I plug in the x is 3, and just as a reminder, this is x, this is y, into the first derivative, I'm going to have 3 times 2 minus 2 times 3 all over 8 times 2 minus 3 times 3, which is going to be 0 over 16 minus 9, which will just be 0. So yes, this is a critical point. We've got a first derivative being equal to 0. That means that now I need to go plug in those numbers to the second derivative. And you'll notice I'm using pink because I'm going to go back to this equation that I already wrote. So d squared y over dx squared evaluated at 3, 2. Now remember, we just found out that the first derivative is worth 0. So that means that in this equation up here, this part of the equation right here is going to be worth 0. And this part of the equation right here is going to be worth 0 because that's the first derivative. So that's going to make my life a little bit simpler when I go to plug in these numbers. So I'm going to start over here. I'm going to have 8 and then the y, which is 2, minus 3, and then the x, which is 3. Now 0 times 3 is 0. So all that's going to be left in this chunk of the problem is going to be the negative 2. Minus. Now I'm going to have the 3 times the y, which is 2, minus 2 times the x, which is 3. And then 8 times 0 is going to be 0, so all that's going to be left is the negative 3 from over here, all over 8 times the y, which is 2, minus 3 times the x, which is 3, squared. Now, you'll notice I kind of was able to make this a lot simpler by realizing that this blue part matches this value that I got here when I plugged in my numbers. So those become zeros. It makes my life a little bit easier. I still need to go through now and evaluate this to determine if I have a positive or negative number. So 8 times 2 is 16, minus 9 is 7. 7 times negative 2 is negative 14. Minus 3 times 2 is 6. Minus 2 times 3 is 6, so that's 0. Times negative 3 is still 0. Over 8 times 2 is 16. Minus 9 is 7. So we have 7 squared, which means we get negative 14 over 49, which is negative. Since this is a negative number, my function is concave down, which means I'm going to have a max. So now all I'm going to do is state my answer and make sure that I justify it. So I would say that the curve has a relative max at the point 3, 2 because of two things. The first derivative evaluated at 3, 2 is equal to 0, and the second derivative evaluated at 3, 2 is less than 0. It's negative, and so we're going to have a relative max, and that's using the second derivative test. Okay. Thank you guys so much for watching. I know that that last problem was quite a doozy, but just kind of be aware that that is straight off the AP test. It's very similar to the questions you're going to see on those free response questions. So it's really important that we know how to work through these longer problems and not give up, because we can do it. Thank you guys so much for watching, and I will see you soon for some